Hello guys and welcome back to my YouTube channel or the Vig Structure Hub. This is a place where you learn, build and innovate. So today I want to solve this problem. So it is problem number 2 under eccentrically welded connection. So the question is on the board and it reads, determine the leg length of the fillet weld for the eccentric connection as shown in the figure below. As you can see, this is an eccentric connection. So it is loaded with 200 kilonewton on one plate at this point, and the loading is placed at 300 millimeter from this center. Again, the welding is 250 millimeter length on the x-axis and 350 millimeter on the y-axis. Again, it has a distance of x1 from here to the center, and also it has 175 millimeter from this point to this center. So let's see how we can solve such a question. So the first thing to note under this diagram, it is a three-sided weld. So the other example we solved earlier, we had four-sided weld, but for this one is a three-sided weld, as you can see. So in your exam, you should be able to differentiate such diagram or such question when given in an exam, because it may confuse you to differentiate between an eccentrically welded connection with four-side welded and three-side welded. So this one is a three-sided welded, and the other one, the first example, was a four-sided weld. So let's see how we can solve this three-sided weld connection under torsion. So solution. So the first thing to determine is the direct shear is equal to P over 2x plus y. So our P is our loading, is our eccentric loading on the plate, which is 200 kilonewton. So 200 over x is the welded side on the x-axis, and the y is the welded length on the y-axis. So we'll have 2 times 250 plus y, which is 350. Then you punch your calculator. The answer is 0.235. 0.235 kilonewton per millimeter. After calculating the direct shear, what follows next is the x1, is to calculate the length of x1. As you can see on our diagram, our x1 is from here to here. So, and we have the formula for x1, which is x squared over 2x plus y. So x1 is equal to x squared over 2x plus y. So our x is 250. 250 square over 2 times 250 plus y. Y is 350 50. So our x1, which imply x1 is equal to, again you punch your calculator, the answer is 73.53 millimeter. So that is our answer. We proceed to IP. So IP is equal to IX plus IY. So IX is equal to Y cubed over 12 plus X Y square over 2. So our Y is 350 cubed over 12 plus X 250 times Y square 350 square over 2, which imply Ix is equal to, so you can punch your calculator and obtain the answer. So the answer is 18.89 times 10 raised power 6 millimeter to power 4. So Ix is equal to 18.89 times 10 raised power 6 millimeter to power 4. So that is Ix. We proceed to Iy. So Iy is equal to x cubed over 6 plus 2x into bracket x over 2 minus x1, close the bracket, then you square, plus y x1 square, which imply Iy is equal to x is 250. So this is 250 cubed over 6 plus 2 times x times 250. You open the bracket, x is 250 over 2 minus x1. x1 is 73.53, then you square, plus y is 350 times x1 is 73.53 square. Like that. And then you punch your calculator to obtain your answer. So Iy is equal to, punch your calculator. So the answer is 5.82. So Iy is equal to 5.82 times 10 raised to power 6 millimeter to power 4. Therefore, IP is equal to Ix, which is 18 0.89 times 10 raised to the power 6 plus 5.82 times 10 raised to the power 6. So the answer will be 18.89 times 10 raised to the power 6 plus 5.82 times 10 power 6. So the answer is 24.71 times 10 raised to the power 6 . So that is IP. So after calculating IP, which is 24.71 times 10 raised to the power 6 millimeter to the power 4, now we proceed to radius. And remember, this is a three-sided weld under torsion connection. So for this case, the formula to get R is not the same as the one for a four-sided, because for a four-sided is 0.5 into bracket x square plus y square raised to power 0.5. But for this case, it will not be like that one. So for this case, the first thing to note, the distance of radius is the distance from this center to where the load is placed. So it will be the distance from this point up to that . So that is our R. So forget about this one. So our R is the capital R. And how are we going to find this capital R? So to find capital R, you will use Pythagoras theorem. The first thing, you will extend this line . So this is 175. So let's call this distance capital X. So R, let me rub here to create more space for calculation. So R will be x square plus 175 square. And then you get the square root. So what is this distance x? To get distance x, first you will divide this 250 into 2. So you divide 250 by 2. So you will get 125 millimeter. 125 millimeter, it means it is the center of this connection. So from here to here is 250. So the center so it means now from here is 125 millimeter. 125 millimeter. And remember, from the center of this connection to where the load is placed is 300 millimeter. So to get this distance from here to here, we will take 125 minus x1 then plus 300. It means if we take 125 minus this distance x1, we'll get this distance. We'll get that distance. So 125 minus x1, which is 73.53. So that is 51. That is 51.47. So distance x is equal to 51.47 plus 300. So the answer will be 351.47 millimeter. So this distance x is 351.47 millimeter. After getting this distance x, what follows next is to calculate the radius capital R and not small r. So capital R, let me do it on the other side. So capital R is equal to 351.47 square plus 175 square in short, the square root of 351.47 square plus 175 square. So the answer is, therefore, which imply R is equal to 392.63 millimeter. So this is our R. This is now our R from here to here. So I want to repeat what I have just done. So the first thing is to determine this length R, and R is the radius from the center of this connection to the farthest point, of which our point is where our force is acting, eccentric force, which is 200 kilonewton. So you will extend this line from here all the way to where the load is acting. So ignore this small r. So don't use small r. Extend from the center to where the load is acting. After that, you will take 250 divide by 2 to get the center of this part from here to here. So if you get the center from here to here, it means from here to here is 125 millimeter, which is the center of 250. 250 divided by 2. Again, we have our x1. So our x1 is 73 point something. We have already calculated our x1. So to get this distance from this point to the center is 125 minus x1. And then to get the whole of this distance x, we'll take this distance, which is 51.47 plus 300, because 300 is acting at this center to where the load is acting. So this is our distance x, which is 351.47. Again, it happened to be our eccentricity, which is E. So our E will be 351.47. So let's proceed. Again, from this triangle, we can also obtain our theta. So you can also obtain our theta. This one, it will be different from a four-sided weld. So for this, we have this triangle like this. So that is our triangle, and this is our theta. This is our distance, 351.47, and this is 175. So you can use this simple basic of sine, cosine, and tangent, SOHCAHTOA. So for our case, it is cos. So cos theta is equal to adjacent over hypotenuse. So this is the opposite. This is the adjacent, and this is the hypotenuse. So hypotenuse is our radius, which is 351.47. So cos theta is equal to adjacent 351.47 over, no, our radius is 392.63. So cos is equal to 351.47 over 392.63, which imply cos theta is equal to 351.47 divided by 392.63. So this is 0.895. So that is our cos. And then we proceed again from there. After getting cos, we proceed to shear due to torsion. Shear due to torsion, which is equal to, So Ft is equal to PER over IP. So our P is 200 times E. We have said our E is this distance from here to here. So this is 351.47 times R. R is 392.63. Our IP is 24.71 times 10 power 6. So force due to torsion is equal to again you punch your calculator to get the answer. So the answer is 1.11 kilonewton per millimeter. After this, we proceed to resultant force. Resultant force, which is abbreviated as FR. So FR is equal to Fs square plus Ft square plus 2 Fs Ft cos theta raised power a half or 0.5. So our Fs is 0.235 square plus Ft 1.11 square plus 2 times 0.235 times 1.11 times cos theta, which is this value, 0.895 raised power 0.5. Again, you punch your calculator to obtain the answer. So FR is equal to 1.324 kilonewton per millimeter. That is FR. Then we proceed to calculate the leg length of the fillet. So let me clear here to create space for more calculation. So how are we going to calculate the leg length of the fillet as we have been told in the question? So we know that force is equal to the permissible stress times area, or you can say the permissible stress is equal to force over area, and then you make F the subject of the formula. So don't cram the formula. Know how to generate formulas from basics principles. So our force here is this resultant force, which is Fr, and our permissible stress. In fact, we have not been given the permissible stress. Assume a permissible stress of 115 Newton per millimeter square. So we know that force is equal to, our force is the resultant force, which is 1.324, is equal to permissible stress 115 times 10 raised power negative 3, then times area of the fillet is 0.707 times T. T is the leg length of the fillet. So 10 raised power negative 3, we are changing this Newton per millimeter square to kilonewton per millimeter square, because this is in kilonewton per millimeter square. So to get T, you divide both sides by 115 times 10 raised power negative 3 times 0.707. Again here, 115 times 10 raised power negative 3 times 0.707. So which imply T is equal to, you punch your calculator to obtain T. So our T is 16.28 millimeter, say 17 millimeter. So you round it to next whole number, which is 17 millimeter. And that marks the end of that question.